Hey guys, welcome back to the channel. So before we begin this video, I would like to apologize for the inconsistent uploads over the past 2 weeks. So actually I wasn't feeling really well, but I am doing much better now and regular uploads will continue. So in today's video, we will look at a recent paper that is SuperBPE, which is making LLMs faster with better tokenization. The interesting part is that the authors improve a language model performance without changing the transformer architecture. Let's see how they are actually doing it. So, as you know, most improvements in large language models come from making the model larger or changing its architecture. This paper takes a different approach. Instead of modifying the model, the authors only modify the tokenizer. Their goal is to represent text more efficiently so the language model performs better while keeping the transformer architecture exactly the same. So let's first understand the limitation of the standard BPE tokenizer. So BPE uses whitespace pre-tokenization. That means that it cannot merge words across spaces. So due to this, a common phrases like by the way, by accident, of course, or for a living are split into multiple tokens. More tokens means longer sequences, which increases the amount of computation needed during inference. Also, this is a problem in languages such as Chinese where there aren't actually any white spaces. So we are introducing an algorithm that is super BP. In this algorithm, we have a transition point T that the T denotes the vocabulary size. So initially we follow BP algorithm only till a transition point, and after which we ignore the white space and start merging common phrases. So for example, by accident or search engine, these common phrases get merged together despite being separated by a white space. So let's see how exactly Super BP works. So initially we begin with standard BP and after we reach a fixed vocabulary size, which in this paper the authors tried three different transition points. That is once was when it reached 80,000, once in 160,000, then 180,000 vocabulary size. And after this point, they remove the barrier of not merging white spaces and this becomes cross space or Super BP. So let's see how the tokenization differs in case of BPE and Super BPE. So for example, if in BPE tokenization we have that sentence we got there by accident and we let it go through, then we might get the following result and each separate word as a single token. But in Super BP, there might be many other sentences where it has observed that by accident was occurring a lot together. So it merged it into one. So this results in fewer tokens with the same meaning in shorter sequences, which results in lower inference time for computations. So here was the initial experimental setup. So we took 8 billion and 11 billion models with and tried different algorithms of BPE and Super BPE. We kept all the other things, that is the architecture, the data set, the vocabulary size, and the context size fixed so that only the tokenizer was changed and we could observe actually how this changing tokenizer was impacting the model. So we took three cases of transition points as I discussed, and we took two evaluation criteria, that is on 30 downstream benchmark, that is on 30 AI specific tasks like maths, coding or general void, and bits per byte for language modeling. So basically if you have a lower bits per byte, then the model is more confident in its prediction. So the results observed was that across the 30 AI benchmark tasks, there was an improvement of 4% on Super BP tokenizer. Secondly, Super BP outperformed BPE on 25 of the 30 benchmarks. And as there was merging across the white space, the inference cost also reduced by about 27 to 35%. So the authors concluded that using a better tokenizer can significantly enhance the LLM's performance. So now one thing to note was that the BPB was of BPE was slightly lower than that of Super BPE. Now the thing to note here is that BP has common words a lot of the times, like the, of, to. So while we were predicting, then these words come a lot more number of times than others. So it's quite easier to predict and result in a lower BPB. But on the other hand, Super BP merges a lot of these words like by the way or by accident and all. So this results in larger phrases and can increase the BPD. But another thing which you can note from this histogram is that the blue line, that is the one of BP, continues much further till the end. So this basically indicates that on extremely tougher words, Super BP didn't make very large prediction errors, and BP made very high amount of prediction errors on very tougher words. So what you could conclude from this is that firstly, better BP doesn't always mean better performance, and secondly, BP performs very well on easier tasks and struggles on tougher ones. On the other hand, Super BP performs decently good on easier ones and performs decent as well on tougher tasks. So the authors also checked scaling analysis. That is, they tried different model sizes to see if there is any correlation with that on the tokenizer. And the key observation was that the performance gains remained nearly the same across different models. And Super BP was consistently performing better than BP on different model sizes. So that was the main observation. So the authors concluded with that Super BP scales well and continues to outperform BP even though model sizes increase. So to summarize, Super BP introduces a simple but effective idea. So it first learns normal subword tokens and then learns common multi-word expressions by allowing merges across spaces. This results in shorter token sequences, lower inference computation, and better performance on benchmark tasks, all without actually modifying the architecture. And that's going to be it for the video. I hope you found this paper easy to understand. If you liked it, make sure to like and subscribe to my channel. Also, let me know in the comments what kind of videos would you like in the future and how I can improve further. Thank you guys.